So let's complete this segment by pointing out something very important that Rudolf Clausius pointed out. He was born in 1822 and he died in 1888, and he turned out to be profoundly important for the development of thermodynamics. And he focused on the fact that when we write the entropy change for a complete cycle, which is dq reversible over temperature, that's identically equal to 0. An irreversible pathway, however, we can look at by again referring to the Carnot cycle, because the calculated efficiency of a heat engine for a Carnot engine is greater than the efficiency of any real engine. And so that allows us then to do a calculation of the integral for dq over t for irreversible processes. Namely, we have for the Carnot cycle, we have q sub h over t sub h plus q sub c over t sub c. And we know that that quantity has to be greater than q sub h over t sub h plus q sub c over t sub c for a real engine in comparison to the Carnot cycle. All right, so now all we have to do is define the integral that comes from those two pathways. And in particular, we can write that the Carnot cycle is the integral around that cycle of dq for a reversible path divided by the temperature. And because the quantity on the left-hand side, q sub h over t sub h and so on, is larger, that means that our integral of dq for the reversible path has to be larger than the similar integral of dq over the irreversible path divided by temperature. So that gives us an extremely important relationship, and that is that if I write the integral in general of dq over t, that quantity is less than delta S when we have an irreversible cycle, and it's equal to delta S when we have a reversible cycle. And as we'll find out when we move into the second law of thermodynamics, that turns out to be of great importance for connecting entropy to the second law of thermodynamics.